Okay, let's get started. So today I'm going to talk about a specific link layer. So last time we talked about the wired link layer, which is Ethernet. And today I'm going to talk about a different link layer, which is wireless Ethernet or Wi-Fi. And for people who want to, act like they know technology, Ethernet is wired Ethernet is often called, it's called 802.3, and Wi-Fi is called 802.11. Now you might wonder what's all this numbering about, what's going on, and there's a little bit of a reason to using these numbers. So I'll talk about, actually let me explain, because the whole enterprise of building computer networks depends upon having different vendors building equipment. Okay, so when you buy a laptop from Acer or Mac, Apple or IBM or whatever, computers by themselves, you don't really care whether they have the same behavior or not. They can have completely different internals. As long as you're running Windows, you don't care, or Mac OS 10, you don't really care, or Linux, you don't really care. With networks, they have to talk to each other. So you have to have protocol, you have to agreement on both sides. If both sides don't agree, it's not going to work. So it's very important to have a common understanding of what the standard is. And if any one manufacturer decides it's a standard, then it's going to be a problem, because then they're going to tilt it in their favor, right? So it's not a good idea to do that. So you want somebody who's a third party who is equally impartial to everybody. And that organization is IEEE for many things. So IEEE is the Institute of Electrical and Electronic Engineers. And IEEE has members from all different organizations, universities, companies, and so on. And it makes standards. And the idea is that whatever standard it makes, if everybody builds to that standard, then you can interoperate. Okay? The equivalent body in the internet world is the IETF, the Internet Engineering Task Force, so similar kind of body. And then for telephone networks, it's ITU. So these are all International Teletraffic Union. So these are three different standardization bodies. So IEEE has many standards. Okay, there's standards for transmission towers and transformers, and there's standards for cables and standards for microwave relay stations, and you name it. Anything to do with electrical or electronics or communication, they have a standard. Their local area network standard is called 802. That's the number they're given for local area networks. And then local area network people got started, and then they started out with 802.3. That was a third subgroup of the 802 group, and that came up with the wired Ethernet and variants and so on we talked about last time. And then the Wi-Fi group was given the subgroup number 802.11, and then they came up with multiple standards, which are in historical order B, A, G, N, and then AC. So I'll talk about them in a bit more detail, because having these numbers, it's so very important to know what these little designations mean. But these all refer to specific standards that came out from the 802.11 group. And if you want to be really precise about it, each of these has a year associated with it. So it's a 1997 version, there's a 2001 version, I think, and so on. AC actually is a draft standard as of November 2011. So as of a few months ago, still a draft standard. N is, there are two standards, and then the current standard is the second version, and so on. So there's a bit of quite a bit of complexity. And in the second break, I'll tell you a little bit of the history of Wi-Fi, where it came from. It's rather surprising where it came from, but we'll save that for the break. Instead, what we're going to talk about today is essentially what goes on in common to all the different 802.11s, and then a little bit about these specializations of 802.11. Okay, so let me start at the beginning and talk about the components of Wi-Fi. So almost all of you have used Wi-Fi or are using Wi-Fi daily. And so the two components of it, Wi-Fi, are what's called the AP, or access point. And on your laptop or mobile device, you have a wireless NIC, network interface card, and they communicate wirelessly to the access point. Okay. Now, actually, Wi-Fi is defined for two different kinds of access types. One is called infrastructure mode, and this is what I've drawn over here, where you have an access point, and the devices talk to the access point. This is what almost everybody uses, but there is something called ad hoc mode, which is not so widely used, but it's defined, which allows the direct communication between the devices. There's no access point involved. Okay, so you can take two cell phones, if you will, keep them side by side, put them both in ad hoc mode, and they can talk to each other. Okay, if you put them in ad hoc mode, I won't say they can, they should. Okay, it turns out that many manufacturers don't bother testing this when they ship the product, so it's kind of buggy and doesn't really work. But when it works, it's kind of nice because you can talk to each other directly using Wi-Fi. Okay, so these are the components of a Wi-Fi system. Now, the access point actually has typically got a wire coming out of it, and so the access point actually has got two network interfaces. One is the wireless network interface card, which corresponds to the wireless link. In addition, it has a wired link, and this wired link is almost always 802.3, that's a wired Ethernet. Now, if you have Wi-Fi at home, most likely what you have is a box, which is a firewall and a NAT box and a Wi-Fi router or a Wi-Fi box. And this wired link typically will be a cable modem, a wire going to a cable modem or a wire going to a DSL modem. And then this is going to be a Wi-Fi, and you'll have a couple of antennas sticking out of it on the side. And that's a very standard kind of a Wi-Fi access point. Once in the corridor outside, if you go around, you'll see these whitish boxes about that far up with two antennas sticking out of them, and they have a wire coming out of them. Okay, so data coming on the wired side is sent out, broadcast onto the air, and then these devices in range can pick it up, and then data going out the other direction is picked up here and sent out on the wire. How do you know which one to pick it up? Well, it's just as a MAC address. It's the same as the Ethernet MAC address. It's in fact looks the same. It has the same 6 bytes. And so the access point puts it out saying, here, I have a frame with this MAC address, and so you could go get it. Okay, and then they go use it. How do these devices know what IP address to use? Very simple. We have DHCP. So when you associate, so we'll talk about association in a minute. When you go to near an access point, you have to do what's called association and say, here I am. And when I talk about security, I'll show you how that works. And when then the access point knows you're there, it then says, here, I'm going to give this IP address to you. And then also it knows what your MAC address is, and then it knows how to send data to you. Okay, so roughly speaking, that's how that works. Ad hoc mode is a bit more complex, and I won't go into it. But this is sort of the sketch of how Wi-Fi works at a high level. Okay, so to summarize, the wired and the wireless Ethernet they're made to look as similar as possible. Okay, so this wireless link appears to be a wired link, and from our perspective, it's just a broadcast link. And once you have an IP address, this typically forms a single subnet, and so they all have the same IP address prefix. And the only difficult part here is to essentially make sure that the devices tell the access point they're present, so that they know what to do. So the access point knows which set of devices is in its neighborhood. Otherwise, of course, the access point has no idea, right? In a wired system, it knows because there's only a handful of ports. Each port is configured. Here, we don't have that. Okay. So the other thing I need to mention here is that you can actually put a bunch of access points together like this off of the same wired network. Okay, typically what this means is there'll be a switch over here, and you'll have 3 or 4 access points. And you can allow what's called roaming. And with roaming, what happens is that a mobile device can go from here to here and continue to use the system without any change. So what it means exactly is that their IP address is the same, which means the subnet actually goes across all of them. So the IP address doesn't change. Okay, and this is what we have on campus today. If you use the EduRoam network, or if you use the campus Wi-Fi network, as you go from building to building, your IP address doesn't change. All that happens is that these access points talk to each other. So whenever this access point gets somebody who says, here I am, the association part, the access point sends a message over to the other access point, the previous access point, okay, because that's in the association message, says, here I am, and by the way, I used to be here before, and this guy validates and says, is that person okay? Are they secure? And if it is, they continue to get access. So what that means is you can start a browsing session on your mobile in this classroom, not during class, afterwards, and as you go to the library, for example, your session continues. You don't see any break. Okay, so this is what we call roaming, and that's again, the details are a bit more complex, but you can imagine it having two parts: association and then this transfer. Okay, so given this high-level view, okay, there is a component. Oh yeah, right. One last thing I want to talk about, which is important, which is that in some cases, setting up a wireless access point is a bit messy. Okay, so I mean, remember you have to get a wire there. Right? So let's say you have a large house, or you're Bill Gates, so you have a very, very large house, and there's one end here and one end there, and running a wire, well, he can't afford it. He only has $62 billion, I found out today. It's in the paper today. So maybe it's expensive to run wires. Instead, what you'd like to do is this. So let me draw a large mansion now. This is my idea of a mansion. Okay. It's a driveway, I guess. And, well, there you go. That's a very two-dimensional mansion. But at any rate, I have an access point here, and I have an access point here. And let's say this is where my DSL modem is. That's that end. And what I'd like to do really is for this coverage area of this access point somehow to be attached to this guy without running a wire. Okay? And I'd like to do this for other access points as well. I want to somehow attach these access points to each other. And you say, hey, wait a minute. We already have wireless access. Why don't we make these access points talk to each other wirelessly? Wouldn't it be nice if you could just take a bunch of access points like this, and each of these provides service to a bunch of, maybe I shouldn't draw these lines here, each of these provides service to a bunch of devices, but in between them, you actually have some kind of a wireless link as well, right? And then only one of them is connected on a wired link. Okay, and such a thing exists. It's called a wireless mesh network. And in a wireless mesh network, you get service from over here using Wi-Fi. And then there's some way of communicating between these guys as well, which is also wireless. Okay, and it's very messy. Okay, it's very messy because, as you think about in the homework problem, any transmission that's made from here is going to be going to these nodes as well as that. And so there's this problem of interference. And we'll talk a lot more about interference in the next couple of minutes. But so anyway, that's sort of the homework problem. Think about what the interference problem is. But wireless meshes have been defined. They were very hot research area, and companies started manufacturing them and so on. But it turns out that it's still cheaper. It's still not cheaper. It's still you get better performance by running a wire because you're sure of what you're going to get. Whereas with the wireless mesh, it doesn't. It's not so well defined. It's not so good. Okay. So there were many plans for citywide Wi-Fi coverage. Waterloo and many other cities said we're going to do wireless mesh networks. We're going to cover the city with Wi-Fi because we're going to use mesh networks. We're going to hang Wi-Fi access points off of lampposts. Lampposts are high above the ground, so they don't have much interference. And they have electricity because they have light. So you have electricity, so you attach a lamppost, and then these guys are going to self-organize, form this wireless mesh. And as you drive through town, you'll have continuous Wi-Fi coverage, so you can watch a movie on your iPad as you drive around the street. Okay. And this is an ideal, a technological holy grail, to drive down the street while you're watching a movie on your iPad. I have no idea why, but everybody wants to do it. Okay. I think it's easier to just run straight into a brick wall and have an accident intentionally than to have it while driving with an iPad. None of them worked. All municipal Wi-Fi efforts have come to a basically dead halt because they don't work. Wireless meshes basically don't work. Google tried to set up a wireless mesh all over Mountain View, which is where Google is based. Didn't work. San Francisco is going to have coverage all over San Francisco. Didn't work. Toronto is going to have Wi-Fi coverage all over downtown Toronto. That didn't work either. Okay. What does work is cell phones. When we talk about cell phones and why they work, next class. But today I'm just going to tell you about Wi-Fi. And basically, anytime somebody says, I have a great idea, invest in my municipal Wi-Fi venture, the first thing you should do is walk away. Okay. Okay, it just doesn't work. And there are some very good reasons why they're based on technology. So I can't talk about that in a bit. Okay. So that is roughly speaking what the components are. I'm going to spend a moment talking about types, and then we'll take a break. I need to tell you a little bit more about what this wireless link is, what we call a link, because it turns out it's not really a link. Okay. So when we consider, so let's take a look at this right here. So I'm going to focus, on just this thing right here. Okay, this wireless link over here. We draw it as a link, okay, and intuitively, what we mean by link is that if you send something, it's going to come out the other side. But the problem with Wi-Fi is it's not really a link, okay, in the traditional sense of the word. And there are two reasons why it's not a link, okay. The first thing is that it's very noisy, okay. So on a typical wired link, we're going to see a loss rate of roughly like 1 in a million or 1 in a billion. Okay, so you send a billion frames, one is going to get lost. That's typical. Okay, so Ethernet is very, very reliable. On a wireless link, you can have a loss rate as high as 90%, even 100%. Okay, so if you turn your microwave on, for example, and you try to use your Wi-Fi at the same time, your loss rate is going to be 100%. Okay. So it's very, very noisy. Okay, so 100% means nothing is getting through. So all the protocols that we use on the wired side, they say, yeah, I'm going to send data, I'm going to get an ACK or whatever. They just stop because nothing is happening. It's just totally dead. So it's as if the network disappears every time you turn your microwave on. Okay, so that's one problem. And the second problem is, or second issue is that we have this notion of channels. And by channels, I mean that on this link, just like a radio, we need to tune the radio to a particular frequency. Exactly in the same way, we need to tune the sender and the receiver to the same frequency. Okay, so you can say I want to be at 2.435 gigahertz, and the receiver has to be 2.435 gigahertz, and then they talk to each other. And if you use a different number, it's a different channel. Okay, so Wi-Fi today is defined to have in different countries different things. In the US, there are essentially 11 channels defined, okay? And so you can think of there being 11 different channels. However, not all channels can be used at the same time. In fact, only in the US, only one, or US and Canada, only 1, 6, and 11 are far enough away that you don't hear each other. So if you transmit on one and you transmit on two at the same time, the receivers are going to be in trouble. So maybe I should talk about that for just a moment. Okay, so let me just talk about this noisy part for another reason before I go into the channels. Let me draw exactly what happens when two stations transmit at the same time. So here are two transmitters. There's transmitter 1, there's transmitter 2, and then here's some receiver. I'll call that RX1. And let's assume that both of these transmitters put a frame onto the air at the same time. And let's say they're on channels 1, both of them on channel 1 at the same time. Okay? This is exactly like a wired Ethernet where two stations are sending at the same time. Right? What happens in Ethernet when you have two frames at the same time? You get a collision, and the receiver can't make out. On the wired Ethernet, everybody hears the collision. Everybody hears that there's a problem, right? Because that's the way that's the way the wired Ethernet is. In the wireless case, the only person who gets interference or receiver, or the only person who figures out there's a problem is the receiver. Only the receiver. So interference happens at the receiver. Okay, so the transmitters actually don't know there was a problem. The transmitter said, yeah, I transmitted it, no big deal. This transmitter said, transmitted it. Only the receiver knows there was a problem. So the transmitters need to be told, okay, if there was a collision. And we'll come to that in a moment, how it's done. But this is extremely important, that the interference at the receiver, only the receiver knows about it. Now to come back to channels, if they're both on 1, there's going to be a collision. If this is on 1 and this is on 2, there's still going to be a collision, okay? It's only when this is on 1 and this is on 6, then there's no collision, and then the receiver has to choose whether to be on 1 or on 6. If it says at 1, then it picks up this transmission, and this one has no effect. If it tunes it to 6, it gets this one, but not that one. And the other channel that's available is 11, okay? Now you can use 2 and 7, but then you can't use 3 at the same time. So ideally, you could have an access point over here, which has 3 network interface cards, each tuned to a different frequency. Channel number 1, channel 6, channel 11. And you can take all the devices and give them different channel numbers, and then they can all be active at the same time. Or I should say, 3 of them can be active at the same time. 1 from 1, 1 from 6, 1 from 11. Okay. So that's the channelization idea in Wi-Fi. Again, that's different from a wired link. In a wired link, you just have a link. Right here, you need to know what channel you're going to be using. So that's one thing I want to talk about here, channels. And there's a little bit of more detail about channels I'll get to when I talk about different types of Wi-Fi. But the important part is it's noisy. I should probably say there's interference. At receiver. Oops. Okay. Any questions about this so far? So to summarize what I've said so far is that the way Wi-Fi works is you have an access point. We have wireless links. And typically you're in infrastructure mode. And infrastructure mode, the next talk to the access point. Typically you have wired access over here, but some cases you can have wireless mesh, in which case you're wireless on both sides. And the wireless link differs from a wired link in that it's quite noisy. You have the notion of channels. And if you have 2 transmissions at the same channel at the same time, then at the receiver you have interference, but not at the sender. The sender doesn't know. So the AP doesn't give a device a channel. Instead, a set of devices share a channel using something like CSMA CD. If you remember CSMA CD, they're all on the same channel. They're all on the same wire, right? So you can think of there being equivalent of 3 wires, 1 corresponding to each channel. And the set of devices share it using CSMA CA, which is what I'm going to talk about later. Okay. Yeah, but they don't use, but they're all on the same channel. So if you're all on the same channel, only one of you can use it. But if you're all on 3 different channels, then only 3 of you can use it at any point in time. But the point in time lasts for about, I don't know, half a millisecond. Okay. So half a millisecond is not a long time. So yes, you have to wait a few milliseconds before it's your turn, but it's not so bad. Okay. Yeah. So I'm going to talk now about these different alphabet soup of numbers, B, A, G, N, A, C, and just give you a little bit of sense of where they're coming from and sort of where they're headed, I guess. So how many of you have seen this 802.11b or G, N? Okay, or maybe I should turn it around. Since how many of you have not seen these designations? 11b, 11g. Okay, a couple of you. Okay, so for those of you who use Wi-Fi, quite often you'll see these designations 802.11b, A, G, N. These refer to standards, and they differ from each other. So 802.11b is sort of the earliest standard, and it's at 1. It was initially defined to be 1, 2, and the current version is 11 megabits per second. So that's a maximum speed is 11 megabits per second, and it uses these 3 channels, or it has basically 3 usable channels simultaneously. Can't use more than 3 simultaneously. It's okay, which are 1, 6, and 11. So those are the 3 orthogonal channels. And okay, so that's basically all you really need to know. 802.11b. It's a bit slow, reliable, And so older chipsets will be B chipsets. Okay, so if you use an access point from, I don't know, 6, 7 years ago, pretty much guaranteed to be B. Yeah, so older mobile devices also will be B. The next one that came out was 802.11a. Now, don't ask me why B comes before A, but it did. A actually goes at up to 54 megabits per second. Okay, and it has actually 12 channels. So you say, hey, this looks pretty good. It can go much faster. It has more channels. But then the difference between B and A is that this is at the 2.4 gigahertz band, and this is at the 5 gigahertz band. And you'll say, okay, so what? You know, what does this mean? What does 5 gigahertz mean? So to understand what it means, let me explain to you what it is. So the gigahertz is the frequency of the radiation, electromagnetic radiation. And so you should know that frequency times wavelength equals 300,000, okay, 3 into 10 to the power 8 meters per second, right? That's the speed of light. So frequency times, so the higher the frequency, the smaller the wavelength, okay? So if you look at 2.4 gigahertz, the wavelength is this much, okay? So it's about this much, all right? And if you look at 5 gigahertz, the wavelength is about this much. I mean, literally, it's about this versus this. You can actually hold out your finger. That's the wavelength of the electromagnetic radiation. When you have a larger wavelength, you can go around corners a little bit easier. Diffraction is easier, and it goes through walls a bit easier. Okay, it goes through partitions, walls, and so on a bit easier. And when it's 5 gigahertz, it's a bit smaller, all right? So it doesn't go through. So here, the range is higher. So if you set up a B access point at your home, 2.4 gigahertz band, you'll actually cover more of your home or your building than you will with the A. Okay. The second issue is what else is on at these bands. Okay. So 2.4 gigahertz band is a band in which both bands actually are bands in which water absorbs radiation. Okay. So where do you find water in a home? Actually, it's a very interesting question. Where do you find water in a home? In all your pipes? No, there's a bigger source of water in your home that's moving around all the time. Water people. You're 80% water. You're big bags of water, actually. Okay, because your life originated in the oceans, I guess. You're big bags of water walking around. So if I were to put an access point over there and try to move it through all you guys to the other end, I wouldn't succeed. Okay, what I'm going to do is to warm up your soft tissues a little bit. It's only about 400 milliwatts, not enough to kill you. You can feel a little bit warm, but you're absorbing the radiation. It's like a microwave oven. In fact, that's how microwave ovens work. Microwave ovens in the 5 gigahertz range, typically. And what they have is what's called a cavity resonator, and you put electricity through it, and it puts out radiation, very high amounts of radiation. When you put in your burger or whatever, your pizza, warming it up, all the water molecules inside the pizza resonate, okay, with that, and they absorb all the radiation, okay, and that's how it heats it up. That's why when you put a pizza in a conventional oven, it heats from the outside in, so the outside gets burnt and the inside is still cold, right, as you know by now. Okay. On the other hand, the microwave, it's evenly warmed everywhere because all the water molecules are absorbing, okay, and that's what's going on. So Wi-Fi is on the same absorption band as water molecules. So why? Okay, what Wi-Fi is doing is it's using a frequency band such that if you send a data signal on Wi-Fi, it's pretty much guaranteed to be absorbed by people, by leaves, by cloud, by fog, by rain, by animals moving past, birds flying through. It gets reflected by buses going through. Any cabinet you'd open, that cart over there, there's a bit of metal on it, it reflects there. Is this a good frequency range to be using? Instead, there's a better frequency range, 700 megahertz. 700 megahertz is a long range. It's not 5 gigahertz. The wavelength is about the size of this room. It goes through buildings beautifully. Not absorbed by people, not absorbed by cats. water pipes, not reflected by metal, transfers about 10 kilometers to 50 kilometers, and these guys go about 30 meters before they die out. They fizzle out in 30 meters. This one goes 30 meters, that one goes 90 meters, that one goes 10 kilometers. Which one would you prefer? 700 megahertz or 2.4 gigahertz? 700 megahertz, right? One is beachfront property, the other is swamps. It's mosquitoes, snakes, poisonous frogs. It's messy, it's awful, okay? You don't want to live there. So why is everybody here? Why are they all in the swamps? Because it's free, okay? In their infinite wisdom, the governmental authorities in most countries in the world decided that for educational purposes, they should give away free 700 megahertz and all these beautiful transmission bands to TV stations, because they broadcast educational content. Like, you can name your favorite show, it's educational content on TV. And so in the 1920s, they decided that this is the best frequency we're going to get, and they went and got the frequencies from the government. So every TV station in the world broadcasts in these beautiful beachfront property, and they all paid for it $0, okay? Because they convinced the governments, we're broadcasting educational content. As soon as they got that, immediately started doing advertising. With that money, they basically paid off the legislators to make sure that they would never lose that property, okay? These bands, the physicists figured out, were terrible. You can't broadcast anything on them, and so they said, we'll call it Industrial, Scientific, and Medical Bands, ISM band, which means it's junk, okay? Take it. Who cares? Just take it. We don't want it, okay? It's pure junk. And they said, do what you want, it's unregulated. And so when people started building these, and I'll tell you the story in 15 minutes of what they were building. They said, which one should we use? Should we try and get some TV station channels, beautiful channels? Government said, oh no, that's for TV, for educational content. All right, fine, we'll use this swampy land, these channels over here. And they did. And from that, they built a multi-billion-dollar industry, okay? So it's a triumph of technology that these channels, which are really, really bad, actually are supporting a huge Wi-Fi industry, right? Because we know we kind of worked our way around all these bad things. The 700 megahertz, by the way, what's happened, again, to give you a little bit of history, is that around 10, 15 years ago, I guess, maybe 10 years ago, a lot of people woke to the realization that, on the one hand, the TV stations haven't really improved their technology for the last 80 years. They still use the same old transmitters and transmission stations. A. B, they're not really doing education by any stretch of the imagination. I mean, they call it de-education, okay? I mean, I've seen these t-shirts that say unlearn on them. Have people seen the unlearn? That just means watch TV, you know? So they're not really, and so they went to different people went to different countries. Google, for example, went to the US Congress and said, hey, why don't you give us some of the TV channels? And so a long-term plan was hatched by which TV would be converted to digital channels, and then instead of using all the space, they're going to use up a little bit less space, and this band would be freed up, okay? And that happened in the US in 2009, I believe, happened in Canada in 2011. So April 1st, 2011, I think roughly, or maybe May 1st, something like that, analog TV was shut down in Canada, and everything went digital, okay? So for those of you who watched analog TV, you had to buy a digital tuner, and so we don't have any analog TV anymore. That freed up the 700 megahertz band, and this year, I believe it's going to be auctioned off, okay? So they're going to sell it for a few, I don't know, $20 billion. That's what it's going to cost. In the US, Google wanted to buy it, and they bid for it, but other people got it. But this property, or this beachfront property, which was given free to the TV stations, the TV stations still own a big chunk of it. But one small part, they were taken away, kicking and screaming, but they gave it up in the end. And these are 700 megahertz. This is what's called, anyway, there's a whole story behind it. But that is coming. So we're going to have extremely high quality transmission. That's going to be part of 4G. Okay, if you heard of 4G, that's actually part of it is in the 700 megahertz spectrum. Nice spectrum, okay? But there's lots more nice spectrum, which is being held on to by the TV broadcast companies. And I hope all of you will realize what's being done to you by your government, by our government, by giving away the spectrum rights to TV companies for free. It's a real shame. Okay, so to come back to this, we have swamp number 1 or swamp number 2, and swamp number 2 turns out to be worse than swamp number 1. And so B is slightly better than A, and so A didn't really quite make it. Nobody uses A anymore because we got 802.11g. And what G is that it's up to 54 megabit per second. Great, that's very good. And it has 3 channels only, and it's on the 2.4 gigahertz. Okay, so this one is on the same channel as there, so it's still in swamp. It's in swamp. This is swamp A, I guess, with 811. It's swamp B. So it's a swamp, but it go faster. It go 5 times faster. So G came out around 2004 or so, something like that. And so everybody who saw B or G, they say, yeah, G is better. So immediately you started getting what are called B/G routers, B/G access points. What that meant was if you had an old device using B, it would use B. But if you had G, you could go much faster. And eventually everybody moved to G. Okay, so that's in a nutshell what happened with B and G. And then the manufacturers got pretty excited because what they figured out was a way in which they could take 2 G channels and kind of move them together, club them together. It's called channel bonding. And this one goes up to 108 megabit per second. That's 802.11n. And this is 1 channel only, so only 1 at a time. But it's also the 2.4 gigahertz. So the idea is that you basically take 2 G channels and you stick them together and you double the rate, and that's what N is. So if you see, so today if you buy a router from wherever your favorite store is, you'll get what's called an ABGN router. Okay, nobody uses A, and your old devices will use B. Newer ones will use G, and then the latest ones will use N. And if you're the only one around and you use N, you'll actually get very good performance. Even though it's up to 108. You'll get about 40, 50 megabit per second, enough for HDTV transmission, okay, from wherever one end of the house to the other, which is really what the purpose was. So if you buy a new TV which has a Wi-Fi on it, N on it, and you have like Apple TV or some kind of base station or even your desktop, you can actually stream on it live HDTV on 802.11n, and there's also, it's much less sensitive to interference. Again, there's a lot of technology I'm not talking to you about at all. It's really like a extremely high-level view. It's like a Mickey Mouse view of the world. There's so much money riding on it. Just to give you an idea, about 2 million of these network interface cards are sold every day. 2 million a day, every day. Okay? So you can imagine that many people are spending a lot of time trying to figure out how it works. And there's a lot of innovation. But the bottom line is that this is what we have right now. Now there is a new standard coming up, 802.11 AC, which is still a draft standard, and it offers even more goodies and even better rates and so on and so forth. And I'm not going to go into it because honestly I don't know much about it. I just saw it that this has been announced, but I don't know the details yet. But I'm sure 2 years from now everybody will want to have AC. But at this point, this is the best. Now, until recently, this was not standardized, so it was called pre-standard Ns. If you bought that, you may be out of luck because standard may be different. But if you buy N equipment today, it is standardized. Whereas if you buy pre-standard AC, again, you're going to be potentially out of luck. Okay, so these are the different types, and they differ in their rate, how fast they go, how many channels available, and at what band they are in. Okay, and that's what gives them different kind of feel. Okay, so that was the types. I kind of mentioned the characteristics already, and I'm not going to mention coding because I realize there's too much on that. So I'm going to talk to you instead about security, because that's something you do need to know about as somebody in IT management, as many of you are. And I'm going to briefly give you an overview of how security works, and then after that, I'm going to go into more details on security after the break. Okay, so let me talk to you about what happens sort of step by step when something enters the range. So let's say here's an access point, and we'll call this sort of the coverage area. Now, many people view the access point's coverage area as this perfect circle. Okay, it's not. Coverage areas are not circles because what you're talking about is radio frequency propagation. How much does a frame propagate when you have an antenna? An omnidirectional antenna is basically a stick pointing into the air, okay, and it just radiates in all directions. The coverage area kind of depends. So if you have hallways, it goes further. If it's a wall, it doesn't go further. So the coverage area is not shaped like a circle at all. Okay. The second thing is it changes all the time, depending on many, many factors. So the best way to think about it is like an amoeba. Okay. The coverage is like an amoeba that's always changing its shape all the time. Okay. Every 30 milliseconds, it changes its shape. So you have this amoeba-like thing, but it doesn't change too much inside the core. Okay. So if you get a device and you walk right into this area, what happens? Okay. So here's the device, and here's the access point. So the access point needs to learn of the device needs to know the access point, and the access point needs to authenticate the device and say, yeah, it's okay for me to give service. It's not some random person, right, who doesn't have permission. So the first thing that happens is the access point periodically sends out what are called beacon frames. And the beacon frame basically announces to the world, here I am, I'm an access point, I'm giving service, my subnet number is this, my MAC is this. There's a bunch of details, I'm on channel so and so, okay? I'm on channel 3, channel 1, whatever it is, that's what the access point is doing. So when you configure your Wi-Fi router at home, you set up the access point, you could say, what channel do you want to be on? You configure that, that's what's going on. And it says, what's the beacon interval? Typically, it's 100 milliseconds. So 10 times a second, you're going to be sending out this beacon message. Here I am, all the time. All day, all night, it's going on, right? That's your beacon message. The device doesn't know what channel the access point is on. So what the device is doing, it's scanning. Okay, it wakes up, it scans, nothing there, goes back to sleep. Wakes up, scans, nothing there, goes back to sleep. It keeps doing that, right? So if you had this experience, you take your laptop, you go into a Wi-Fi hotspot, as they call it. There's no signal, you wait a few minutes, suddenly your thing lights up. It's not instantaneous, but it takes a little bit, that pie kind of shape to light up, right? It takes a few seconds, takes a few minutes. That's because it's scanning. Scanning channel 1, nothing, channel 2, nothing, channel 3, oops, I got something. Okay, this is access point on channel 3. Keep scanning and says, okay, I found something on channel 6, found something on channel 7. What are the signal strengths? Some of them are stronger. Okay, I'll try and choose one. Okay, so device is scanning, and the AP is beaconing. Okay, it's sending these beacons. Once the device has picked an AP, knows of a beacon, what it does is it sends an associate message. Actually, it sends an authenticate message, which basically says, here I am, and that's part of security, which says, I'd like to use your services, and this is my credentials, and if the credentials are okay, then the AP basically says okay. And then it sends an associate message saying, okay, now I'm part of your network, okay? And if you've ever seen, there's something called the basic service set, and basic service set, or BSS, is basically, it's a set of devices that are associated with the access points. If you ever use an AP, it's what's your BSS? Well, that's your BSS. So that's your scanning associates. At this point, basically, data transfer can happen, okay, between the device and the access point. Because after these two steps, the access point knows its device is fine, the device knows the access point, and it knows what channel it's on, and now we can actually start using each other. How it uses it is CSMA CA, which we'll come to after the break. And the security part is what's happening over here. Okay, there's what is the authentication mechanism by which the device and the AP know that each other is valid. Because after all, the AP could be masquerading. You can take your laptop and say, I want to be an AP. You can become an AP. Anybody can become an AP. So how do you know they're okay, right? Because they could say, I'm an AP, give me a login, give me a password, and then you can play what's called man-in-the-middle attack. And you take all your data, give it to the actual AP, and you're sitting in between sniffing everything. Okay, and if you do that, you can get everybody's logins and passwords. It's not just a hypothetical thing. If you go to DC library, there's always a few trolls, who call themselves EduRome or EdRome or whatever, right? Mike is laughing here. You've seen these. There's always a few of them around, so be careful. So let's take a look over here, and there are kind of two issues with security you have to worry about. Okay, so one of them is having to do with over-the-air privacy, right? So, so what this means is that if I'm sending data over the air, anybody with a receiver tuned to that channel can listen to it, right? So if I'm sending whatever information on that, what's to prevent other people from listening to it? Okay, so obviously we need to somehow encrypt everything that goes over the air, okay, and that's what is actually done. So everything that's sent over the air is encrypted. And then the second thing is authentication. So we need to make sure that somebody using the access point is actually allowed to use the access point, that they have the permission to use the access point. So these things are solved in different ways, okay, they're solved in different ways. So for over-the-air security, what happens is that in this authentication phase, as part of the authentication phase, the access point tells the device, I'm going to use this particular key. Okay, there's sort of a secret that's shared between the two. And so the easiest way to understand this is when I talk about what you do at home, right? So when you create your access point at home, you create a password for it, right? You create a password, it's the Wi-Fi password for it. And then the same password has to be given by on the device, okay? And then this allows the device and the access point to have a shared secret. When they have a shared secret, what happens is that in the authentication phase, the device tells the access point, okay, this is the password, and the access point says, okay, that's fine, and then it uses that password to encrypt what's called a session key, which is a one-time key that's used for the communication, okay? And that's basically what's going on. So the details of this, actually, Andy will be covering next week when he talks about security. He'll talk a little bit more about how that works. But that's over the air, right? So essentially over here, you're going to send your password. And then you get back over here in this OK message, a session key. At this point, by encrypting everything with the session key, you're going to get over-the-air security, and that's okay. The second part is authentication, which is that in the home case, authentication is easy. Okay, if you have the password, you must be using it because nobody else is there. But what about here, right? What happens over here is that we actually need to use, for example, to use the Waterloo EduRome, you have to give your UW credentials, your what I am credentials, right? You need to give your login and password, and then that gets checked somewhere else. So what's happening over there is that this access point is connected via a switch to what's called Authentication Server. And this authentication server, so what happens is that the device associates the access point and says, here's my login and password. And that's sent in a special way, okay, which prevents anybody from snooping on it. And that goes over to the authentication server. The authentication server looks at the login and password, says, yeah, that's okay, and sends an okay message back to the access point. At that point, the access point tells the NIC, okay, you're fine, you can use it now. Okay, so there's this additional step of authentication. And this is what we do in any, what we call enterprise wireless network. Enterprise wireless LAN, we always have an authentication server because all the employee credentials, everything are kept in one place. In our case, we use what I am as the server. And so this server is contacted by the access points in all the hallways whenever somebody tries to sign in. And so the login and password from here are sent by the AP to the authentication server and comes back over here. Okay. Once it's done, once it says okay, then you have over-the-air privacy as before. So we have kind of two parts joined together. One is the authentication of the user, and second is the over-the-air privacy, and they're both done using this. So the first part over here, by the way, is the two. One was called wired equivalent privacy was the first one. So this was sort of marketing speak. People said, hey, this wireless stuff sounds good, but I don't believe it's secure. How do I know it's going to work? I don't think anybody, I'm not sure people can't sniff on it. So they said, no, it's just as good as wired. We call it wired equivalent privacy. Okay, this was called WEP. One of the things that researchers found out was that it was not equivalent to wired. Actually, it was very bad. It was very, very bad. So this was all marketing. So Professor Ian Goldberg, who's actually in the faculty here, as a grad student, he actually broke this. And he showed that WEP is really bad. In fact, it can be broken in about 30 seconds using his algorithms. And so they said, oops, it's not equivalent to wired. We're going to do something else. We're going to call it WPA. And I think I forget what WPA stands for now. Wireless privacy. I don't know what it stands for anyway. And the current version is WPA2. And WPA2 is actually pretty good. Okay, so if you use WPA2 or WPA, you're okay. If you're using WEP, don't. Okay, it's very, very bad. Okay, and you can download a sniffer for WEP. There are many sniffers available. And if you just download them, you can break anybody using WEP in about 30 seconds. So it's not even worth using. It's practically unencrypted. Okay, so use this over here. And then, as I said, more details will be in Andy's lectures next week. Okay, that's really all I wanted to say about security at this point, to show you that there are two separate things going on. Any questions about this over here? Okay, so I'm going to now keep that up. I'll take this off. I'm going to show you a little bit about CSMA-CA. And for that, I'm going to go back to the link. Okay, so let's focus for a moment on the case when you have two transmitters. And they're both transmitting to the same receiver on the same channel. Okay, and it's both transmitting at the same time, and they're both transmitting the same channel. And so we have a collision. Okay? All right, so what we'd like to do is, if you have a collision, okay, so what should the transmitters do when there's a collision? What happens in the wired case when there's a collision? After a random backoff, right? So what you do is you say, oops, there was a loss. I'd better back off, but we shouldn't use the same back off if it's going to keep colliding over and over again. So we're going to choose a random interval and back off, right? Here in this case, they don't know there was a collision. They just sent it out, and oops, there was a collision, but only the receiver knew it. So what do? What can we do? Right, we can send back a collision message. So receiver knows there was a collision, right? So receiver knows there's a collision, but it didn't know where the collision came from, right? But it's okay, it's a broadcast medium. So the receiver is sitting there, it gets a garbled message, it says, oops, somebody had a problem. I'm going to broadcast this message that says there's a problem. So we have essentially a message going back that says a collision, okay? So we could do it this way, but the way it's actually done is not that. Okay, the way it's actually done is to change it a little bit. Instead, the sender sends a data message, and it expects back an ACK. Okay, if it doesn't get an ACK back in some period of time, it says there must have been a problem. Okay, so it's like sending a collision message. Okay, but it's not. It's an explicit ACK. And there's some good reasons for it. I'm not going to go into that. But the way that 802.11 does it is you send a data, you get an ACK back. If you don't get an ACK back, you know that there was a problem. And the thing is, you know pretty well exactly when the ACK is going to come back. It's not a many hop network. It's just a one hop thing, right? So it knows it takes this much time to get there, about 10, 20 microseconds. It's going to come back in another 30, 40 microseconds. If I don't get an ACK back in this time, I must have lost. Okay, there was a collision. So now I'm going to back off and try again. Okay, so the first, so compared to the wired, so wired versus wireless. Or 802.3 versus 802.11. One is you have an ACK. Okay, you have an explicit ACK message that says that I got data through. Okay, the second difference is that these guys turn out to be a bit paranoid. They're saying, I'm really not sure nobody else is transmitting. So what you do is that even before you send the data, you do a random backoff. Okay? So what does that mean exactly? What that means is this. When somebody is transmitting, you can certainly hear them. So let's say that TX2 was transmitting to RX. Okay? So TX1 can hear that. Okay? So it hears it, and at some point, the signal ends. Okay? Some point, signal ends. Now, in the case of a wired Ethernet, when the signal ends, you're ready to go. You can go right away. There's nothing that stops you. Just go ahead and use it, right? Because you know there's a jam message. You'll get a message. You'll know very quickly there's a problem. In fact, in a wired Ethernet, the collision can be detected with just a few bits. About 10 bits of data is sent, and within 10 bits, you know there's a problem. You're going to get a jam message right away. So it's, you kind of, it's like you're going through the traffic intersection, and few milliseconds after a collision between the two cars, they both spring back, okay, and try again. So it's not a big deal to have a collision because you go back so quickly. In the case of Wi-Fi, it takes a while. The cars kind of get all mashed up, okay, and then you realize there's a problem. Then you reincarnate. It takes a long time, okay. So you don't want to have that happen. You want to be very cautious. So what happens is this carrier signal stops. When the carrier signal stops, the light turned green, okay. So both cars are heading now towards this. And if the light, if there are many cars all waiting for the light to turn green, carrier is off, they're all going to definitely collide, right? It's guaranteed. So what they do is the light turns green and they all toss a coin. All right? They all toss a coin and they say, okay, I'm going to pick a number between 1 and 10, for example. I'm going to count down. So one guy tosses a coin, picks a 7. The other guy picks a coin 3. Other picks a coin 8. And they start counting down 3, 7, 8, all the way down. The guy who picked 3 goes to 0. He wins. In through the intersection, no problem. Okay? That's exactly what's going on. So we have this, okay. We have this essentially random backoff before transmission. Okay, so actually I'm going to maybe illustrate it with this because this makes a lot of sense. So this is wired Ethernet, okay? So you have an intersection, right? This guy's going like this, other person going like that, and this is a collision, okay? We don't want a collision. So in the wired Ethernet, they're all watching the intersection to see if it's free. When it's free, they both say go, boom. But they're wired, so the few bits, they back off right away, right? They go, just back right off. There's no problem, right? In the case of wireless, if they had a collision, they're going to sit there, there's going to have to call the police and the ambulance and all this other stuff, and then they slowly go back, okay? And then if you have 5 people all waiting for the intersection, if the light goes off, big pile up, okay, the whole bit, and then they slowly back off. So they say, okay, what we're going to do is this. When the light goes green, I'm going to assume somebody else is going to go through as well. Let's do a random backoff. So let's say this picks 5, this picks 3, goes 5, goes 3, 4, 2, 3, 1, 2, 0, boom, goes through, no problem. This guy freezes the timer at 2. Freezes the timer at 2 because some other guy comes here, he's going to pick a value between 1 and 10, but this guy's still at 2. So this guy picks 7, 6, 1, 5, 0, boom, I go through. So by having waited earlier, it gets priority. Okay, it's a nice little scheme. If you picked a number earlier, when somebody else goes through, you hear them. You say, okay, I'm going to freeze my timer. And then it goes through, and you keep going down. Somebody else may go through, but chances are pretty good that you will hit 0 before anybody else. So this gives a nice fairness property to CSMA-CA. Correct, that's right. So when the transmission is over, if you've frozen the timer, you start counting down from there, but everybody else, no, sorry, not everybody else. Everybody who started new, but all the other people could also freeze the timers, right? But they clearly, one of them is going to win. But it's unlikely that they're going to have this problem. They're not going to have pileups anymore. What's going on, though? It's wasteful. It's wasteful because guess what's happening? It's free. You're the only person there. There's nobody else. But you imagine there's somebody else. You say 7, 6, 5, 4, 3, 2, 1, 0. Go through. Oh, nothing happened. Great. Pick a number. 9, 9, 8, 7. There's nobody else there. There's nobody else there. And so, Victor, your question, why is it not 108 megabits per second? Because this guy is paranoid. He's just sitting there counting down to 0, there's nothing happening. Okay? Because CSMA is paranoid. Okay? It thinks that something is going to happen anyway. And when something does happen, it's a microwave oven. And guess what the microwave oven does? It's not counting down to 0. It just goes on. Boom, boom, boom. It's going through all the time through the intersection. It's saying, oh, can I go through? No, 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 no. And then the microwave oven got 2 minutes. And this guy is sitting there, oops, I'm sorry, I can't go through. It's really wishy-washy little thing, you know. But the microwave is like a tank. Just roars right through the intersection. Okay. And that's why you don't get 108 megabits per second. You're like, can I go? No, no, can I go? So that's Wi-Fi for you. It's like, please, can I go now? I'm counting down to 0. Okay? Whoop, no. So you can learn a lot with 2 dusters about Wi-Fi. And that's the way it works. Okay? And so the ACK tells you that you actually went through. And the random back-off before transmission basically, now what happens if you have a collision after random back-off? You do the same thing, you double your back-off. Okay, and if a collision, you double it. So you're going to actually be even worse.
What is TX?
Oh, transmission, sorry. On collision. So the same trick that we use for collision is actually used before the sending. That's what CA. So what does CA stand for? Collision avoidance. Okay, and the collision avoidance algorithm is this thing that says you're going to have everybody kind of back off before they even access the medium. Okay, so I have time to talk about one last thing, and then I'll stop. And that is a little bit about prioritization. And so this is the way prioritization works in Wi-Fi. So let's say I'm drawing on this axis, I'm drawing time. And I'm going to draw sort of this is sort of carrier detect. So that means I'm hearing something, okay? Carrier ended at this point in time. What's going to happen is that for a certain amount of time, I'm going to actually wait, okay, for some random back-off. So it's my random back-off. So okay. Actually, I take it back. I'm sorry. I'm going to do that first. So there is a period of time over here. I'm going to call this IFS, interframe spacing. And then you have the random backoff. Actually, I'm going to double check this in a moment. Can't remember which comes first. But let's just assume this is what it's true. It's either this or the other way around. What's important is this notion of interframe spacing. It's a number, okay? And that number says how long you must wait before you start the random backoff. So not only do you back off, you also have to wait a little bit. Why you do this is because you can choose this value to be small, medium, or large, okay? If you choose a small number, then chances are pretty good that your backoff is going to start here, okay, and may end sooner. Whereas if it's large, you're kind of pushed over. So if you choose a small interframe spacing, you give priority to that transmission, okay? Because you're not going to go through quickly. You're not going to back off so much, okay? So what happens is that we can compute or we can control the priority to which different nodes are given access to the. Can you shut the door for a moment? So by choosing this interframe spacing value, what we're able to do is to give some priority. So typically what happens is that the access point is given high priority. And so it chooses a short interframe spacing. And so it waits only a short period of time before starting its random backoff, whereas somebody who is a regular sort of device will use a large interframe spacing. And so they're going to wait a longer period of time. So the access point basically always can go first. And that's the trick we use for prioritization. And that's another thing that's actually put into CSMA-CA. So the bottom line is that by wasting different amounts of air and by allowing people to wait shorter periods of time, we can give prioritization, and we can also avoid collisions. And avoiding collisions turns out to be both the big win from CSMA CA and also a big problem because it wastes the air.